Let's take a look at the answers for section 1.1.2, these labs. We'll take a look at this, and this is just a discussion in case you want some help being talked through each one. Now, I've got screens like the one you see that will separate each of the labs so that if you want to skip to a particular lab, you can just move your slider on the video until you see the next little title screen pop up, and that way you can skip. So here we go. We'll start with Lab A. Lab A was Perry in his hot tub. So let's go to the solution. Now with Lab A, Perry had 36 tiles and needed to arrange them by length and width in order to create little platforms for his hot tub to sit on, like a patio. So, we had to look at all possible sizes, even the stupid ones. So a length of 1 and a width of 36, like really? How do you put a hot tub on a long string of 36 tiles all in a row? But it is a possible rectangle, so we put it down. Same with like 2 by 18, even 3 by 12. Those just feel like they're not realistic, but it didn't say realistic, it just said possible. And then 4 and 9, 6, and 6. Now you'll notice as we keep going, we start repeating answers, only flipping them. So 4 and 9 becomes 9 and 4. And that's really because in the real world, that would be like saying you're looking at the platform and it's either going 4 across and 9 back toward like a fence, or 9 across and 4 back toward a fence. It's really the same size patio, just turned a different way. But we do need to treat that as separate variables here for the purpose of graphing. Now, in case you're wondering, where did I get my numbers? Well, 36 tiles is an area. That means that when I have the length and the width, they have to multiply to 36 because otherwise I wouldn't be able to organize them into my rectangles. So now I go to graph this, and it asks me, should I connect the dots? Well, no. You shouldn't. Perry's working with whole tiles, and if we connected the dots, we would imply that he would or could be cutting his tiles into different size pieces. And that's not a good idea. Tiles do break when you try to cut them, and that's why when you actually were trying to build something like this, you'd get more than 36 tiles if you were going to cut in case you break one. So because I can't connect the dots, but I want to see the shape, I'm going to use that dotted line or curve in this case. You could also use like a yellow highlighter, something that's sort of there, but not really. So here was my little hand graphed picture. I counted my axes by 3 per square because I had large squares on my graph. So what function family? Well, when I looked at my what's my family, it looked as though this could have been inverse or exponential. But when I looked more closely, this was the inverse family. And the reason I know is that this particular thing, like length and width go together by a multiplication, it doesn't feel like there's any exponent that would be involved in the math. So that means that I don't think it can be exponential because, exponential means exponent. So it's inverse. Now, Perry wants to put a little border around the tiles so that when you're mowing, you don't like chip it with a lawnmower. So it gives it kind of like a little border. And he wants to know which option would mean the least amount of border that he'd have to purchase. And then we were going to show it by showing all the options. Well, a border is a perimeter. So to get the border amount, I'd have to add around the dimensions of each rectangle. So if he did do these stretched 36 tiles in one long row, he would need 74 feet of border in order to do this. As you keep going through, you get to where the minimum amount is if he makes his tub base a 6 by 6 square, because then he only needs 24 feet of border, 4 sides all being 6 feet long. So that's pretty significant compared to the 1 in 36. All right, Lab B. Now, Lab B was about our sick people, And this was a particular flu in this story, but given what we have been living through these recent times, this is definitely a very good question to look at. So we're looking at the growth of the infection. Now, if you've been researching the COVID-19, there's this idea of something called the R factor. And if you've been reading on this, you'll notice that epidemiologists would say the lower the R factor, the better you are in growth of a disease. So in coronavirus cases, they say if the R factor can be less than 1, that means that it's not spreading very quickly. An R value of 1 means that every sick person infects one other sick person. Now, in this particular problem, this particular flu would, epidemiology-wise speaking, have an R value of 2 because each sick person infects 2 other sick people. And the thing is, the sick people who started the whole thing are still counted in the total number of sick people. So that's why day 1 is 6. Velma infects 2 sick people. So now her and her 2 new sick buddies make 3 people. Stanley does the same. He infects 2 people, and now he's also sick. So there's 3. So that's a total of 6 sick people after just one day of them being out and about without their masks. Now, go to day 2. If you assume all 6 of those people perhaps don't know they're totally sick yet, and they're out and doing their thing, and they're not wearing masks or distancing or anything else, well, now you'll end up with each of those sick people makes 2 more people sick. That's 12 additional sick people, plus the original 6. Now, day 2, we have 18 sick people. You will start to see a pattern here. And once you start to see that pattern, you can complete the table. Kind of scary how fast those numbers get big. So if we graph this table, should we connect the dots? Well, no. We're talking about sick people. This is kind of a yes-no, a very binary thing. You either have this flu or you don't. There is no being 0.64 sick or being 11.2 sick people. So we're counting. And when we count, we don't connect the dots. So there's my flu graph. And I used the dotted curve just because I wanted to see what the shape was. And when looking at what's my family, clearly that was exponential. That sort of slow, flat in the beginning, and then all of a sudden around day 3, 3.5, it starts to shoot up really fast. That is the hallmark of the exponential function. Now it says that the scientists in this town will have a vaccine ready for their non-infected people on day 7. So how many people will get the vaccine? Well, if the vaccine is only given to people who've not had it, because people who have the flu would already have the antibodies, a vaccine introduces the virus into your system, forcing your immune system to make antibodies, but without making you sick. So it tricks your immune system into thinking you're sick without the side effects. So if you've already had that flu, you already have antibodies for that particular flu, so you really wouldn't need the vaccine, at least not right at first. So if we say the vaccine is only for the people who've not had the flu, if we look at our table, nobody needs the vaccine by then. It's too late. There are only 3,800 people in this town, and by day 7, they will all be sick, and it will be spreading to their neighboring towns. So there'd be no purpose in a vaccine for this town. Of course, the vaccine would be useful for people outside of this town, but not here. Using my graph table to estimate, I decided to use my table because my graph I just couldn't make big enough. It looks like it's around 6.7 or 6.8 when 3,800 people are infected. So somewhere near the end of the 6th day is when we would cross over to the whole town being sick. Lab C. Now, Lab C was the signature one. Now, do keep in mind, everybody's results will be different. So these are my results, having timed my signature. So it's okay, if your numbers are a little different. I got these numbers, and it said, well, when I graphed the table, could I connect the dots? Actually, on this one, you could, because you could have stopped me at second 8, and I would have been partially through a signature, and we could have measured what part of my signature was on the paper. So I could have a partial signature, and I could stop or have partial seconds. So I'm going to connect the dots here. Now, my dots didn't connect totally great, but I sort of connected them. And in doing so, it actually looked pretty linear, almost like I've got a pattern to the way I sign, and that I'm fairly consistent in the amount of time it takes to sign each of my names. So let's say now I'm the real estate attorney, and I'm going to book the conference room for closings. I have the conference room. I want to get a 10-minute break. Each closing requires 40 signatures. So in my results, it was showing that I take just over 3 seconds to sign one time my name. So 40 signatures would take me a little bit over 2 minutes if I was doing them one right after the other. Now in a closing, that's not how it works. It's not that you have 40 blanks and you fill them in one right after the other. It's usually a blank or two per page. So you have to read the page, you have to explain it, the attorney has to answer questions. So even if you read fast, that's probably 20 to 30 minutes per closing. And then if you add in 10 minutes for a break, it means that you got to estimate on about 40 minutes for each closing. From 9 to 5, that's a total of 8 hours, which is 480 total minutes. So at most you could have 12 closings. And me personally, I'd schedule 11 and I'd make that 12th empty slot my lunch break. Knowing that sometimes these would finish early, I know I can schedule like a coffee break or a bathroom break. So I'd schedule 11 closings per day. Next up are labs D and E. These were enrichments and optional. So if you didn't do them, you can go ahead and stop your video. If you did, here we go. Lab D was the habitats for the homeless. So the first thing I needed to do was figure out how many total hours a community of 15 houses and a community common area would take. So 15 houses at 480 hours per house was 7,200 hours. And then if I added that to the 1,000 hours to do the community area, I have 8,200 total man hours to complete the neighborhood. That just means that if I were paying everybody at the end of this project, I should have paid for 8,200 hours of work. Now, some people will get more of those than others. So if I look at the crew size, if, like me, by myself was going to do the entire job, it would take me 8,200 hours to do it. If you up that to 5 people, of course that drops the hours because now those 5 people share the 8,200 hours. So 8,200 divided by 5 would be 1,640. And so on and so forth. So you go up to 100 people on the crew, 100 people dividing the total hours means everyone would give 82 hours of their life to do it. And if you could get 1,000 people, then theoretically it would be 8 hours per person roughly, and that's not bad. Now, when I graph this, should I connect the dots? No. You can have people work partial hours or partial days, but you can't have part of a people. So I'm going to use the dotted again, and boy, I had to really mess with my graph. I used the little compression because this thing was just huge. So I used the little compression and started my graph at 400 hours, and that was because I only did a crew size of up to 20. I just didn't think I was going to be able to fit the crew size of 1,000. But I did get that same curve that I've seen before, which is an inverse function. Now here comes the big part. The problem with building homes is you have to do things in certain orders, and then things can't be done, and certain things can't be done until other things are done. So like your plumbing and your electrical has to be fully installed and inspected before you put up the drywall. That's the boards that make a wall solid. And you can't paint those walls until they've been installed, and then there's this thing they call taping and mudding. So when two sheets of wall sit side by side, they fill it with like this goo paste. They call it mud. It's like clay. And then they put a piece of smooth tape over the top and then put more of the mud, and then they have to let it dry and sand it. So like there's a lot of stuff where there's going to be some lag time. The painters can't even come in until a bunch of things are done. So for that reason, you need at least 10 days, and that's at max people working. You would need 10 days to finish this. A standard working day is 8 hours. You really can't expect people to work on the weekends, so at most, you can only expect 5 days per week that people are going to work. Some people might only work on weekends, so they only work 2 days. So what crew size would you need to finish this before December, assuming it's now about September? If you assume that a crew will work each working day till the project's done, September to December is about 3 months, call it 12 weeks. So now, if you were going to try to do this in 10 days, 10 days of 8 hours per day is 80 working hours. If I look at my table, if I were to ask each person to do 80 working hours, I would need about 100 people, and someone would have to put in a couple extra hours here and there. So 100 people to get it done in 10 days. Now, if I stretch that out to 12 weeks, well, 12 weeks at 5 days per week at 8 hours per day is 480 working hours. And if you were going to ask people to do that, just share the load, then a crew size of 17 to 18 could get the job done because they could do 480 working hours, just spread out over 12 weeks at 5 days per week and 8 hours per day. Now, realistically, we of course know the more people you could get there, the less each person has to do. So larger crew sizes are going to mean a smaller job time. But keep in mind, these are volunteers. Volunteers often have other paying jobs, so they can only give a few hours per week. So even if you assume each person could only volunteer 20 hours per week, not 40, that doubles your needed crew size because now you would need 2 people to complete what used to be the weekly work of 1. So now if you need a 10-day completion, you would have to have at least 200 people. And for a 12-week completion, you need at least 34. Then you start figuring in, well, what if people only volunteer on weekends? That's only 16 hours, 8 hours a day, 2 days. What about rain delays? If it rains for a few days, you might not be able to work on the building of the house, or a holiday, or severe weather. A lot of things that might shorten your available work days in that 12 weeks. So, of course, every time you shorten the amount of time, you're going to have to increase the crew size to match. And now to Lab E. Lab E was Chernobyl. This is real, which is why I gave you the link to the article. And there were 2 main radioactive elements that were released into that environment. And so iodine-131 has a half-life of 8 days. That means that half the iodine will sort of dissolve into the atmosphere or decay every 8 days. And then the cesiums have half-lives of 30 years. So that means it takes a 30-year time period before half of the cesium has decayed off. Depending on which you chose, you had to make a table. So the percent remaining in each of these tables would be the same because the way you're going to count your table is by half-lives. That's the easiest way to do it because I know for iodine that if at day 0 there's 100% of the iodine, I know for sure on day 8 there will be 50% because that's half-life. I can't tell you much about days 4, 5, 6, but I know day 8 will be at 50. I know that 8 days after that, day 16, it will be now half again. It'll be at 25, and so on and so forth. The exact same pattern holds true for cesium, only in this case the time span is counting by 30 years. So would we connect dots? Absolutely. This is a constant process, and you can have partial percentages and partial days, times, or years. It's continuously decaying. So I graphed each table in Desmos. So iodine's the purple and cesium is the orange. And these are both exponential. When you think about half, that feels like a multiplication or division kind of thing. This really is exponential. You may have said inverse, but trust me on this one, it's exponential. Now, let's see if we could figure out how much of that radiation would still be there now. Well, Chernobyl melted down on April 26th of 1986. If we take that time, so 5 months from April 26th to September 26th, which, yeah, that's like maybe a month from now, but it's okay. Call that 5 months, and then 34 years to get to September 26th of 2020. So 34 years and 5 months comes out to a little over 12,000 days. So for iodine, if it's 8 days for every half-life, then it will have done a half-life 1,571 times since Chernobyl melted. The graph, if you look, would get so tiny by the time you count it out to 12,568 days. It's a good bet that if there's any iodine still there, which actually there still is, but it's no longer detectable, it will really tell you how much there is. Now, cesium, being a much slower decay rate, in that amount of time, 34 years and 5 months is about 34.4 years. You've only been through 1.15 half-lives. If I look at the graph, 34.4 years, let's see, so that's 100. It looks like it's counting by 20, so 20, 40, 60, 80, 20, 40, 30, 30.4. That's on iodine would be if this were days, but for cesium, this is years. We're up here. That's interesting. So 34 years. And at 34 years, whoops, that should say a little bit over 50%, or a little bit under 50% of the cesium is still present. So go ahead and make that change. I'll fix that on the sheet. That it's a little bit less than 50% is still there. That's crazy. So that's the end of our solutions.